Okay, so we've come to the end then of chapter 2. Again, a very short chapter, just the the 4 sections. The first 2 sections were all about limits. Section 1 was finding then the limits as x is approaching a specific value a, and then using the different algebraic techniques to compute a limit. Section 2 then was limits that involved infinity, which brought about our asymptotes. We had a vertical asymptote at x equals some particular value a if the limit was equal to the infinity. We had horizontal asymptotes if the limit was equal to some constant value as x was going to infinity. Okay, so vertical asymptotes are when your limit equals the infinities. Horizontal asymptotes are the limits as x goes to infinity, if there is one. And then we talked about the end behavior with that as well and saw that on the quiz. Section 3 then used the concept of limits to help us determine if functions were continuous. If a function was going to be continuous, then the limits had to exist, and it had to be the same as the function value. And then moving into section 4, we used the limits to find a limit of what we call the difference quotient, which is just calculating a slope. And then we use that limit of the difference quotient to represent our slope of the curve, our slope of the tangent, our instantaneous rate of change, and again, obviously, the limit of the difference quotient. Okay. I want to first go back into page 92. Are there any last questions we have out of anything from the text on 92, from the 2.4 homework? Any last questions there? Good with that one? Okay. Into the graded homework from last night. Do we have a couple of questions off of the graded homework from last night? 2? Okay. Basically, 1 and 2 are kind of asking you domain-type questions. If we've got a rational function, if we've got a fraction, your function will be undefined wherever the denominator is equal to 0. Well, the second red flag for domains are radicals. What type of number can we not have under the radicals? What type of number down there will not give us a real valued solution? Negatives. So what we're going to do on number 2 is we're going to take that radicand, that 4x plus 5, and set it so that it has to be positive. So what kind of an inequality will we set up there? 4x plus 5 has to be what would state that it is positive? Yeah, greater than. Now, can it be equal to 0 as well? Yeah, in this case it can, because the square root of 0 is 0. But what if that radical was in the denominator? Then could we set equal to 0? No, then it would only be greater than. So here as we solve this out, we find out that x has to be greater than or equal to negative 5/4. So that's the domain of this function. Our domain is strictly greater than or equal to negative 5/4. So we go from negative 5/4 to infinity. Okay. So that's where the function's defined. That is where the function will be continuous. So answering the question then is, where will it be discontinuous? Where will any discontinuities occur? Well, the discontinuity will occur then when x is less than 5/4. And it's not really a type of discontinuity. It's just that those values are not in the what? They're not in the domain. Okay? So in part C, it's not a jump discontinuity. In part B, it's not an infinite discontinuity. But we're looking at part D. We're looking at all values of x that are less than 5/4. And it's discontinuous down there because those values are just not in the domain. This function, if you were to graph it off, right here is negative 1. So right about here would be negative 5/4, negative 1 1/4. And then it gradually increases as we go to the right. So on its domain, from negative 5 force to infinity, it's continuous. But it's not continuous over here in this area because those values are just not in the domain. Okay with 2? Okay. Anything else from the graded homework last night, folks? Okay with the limits of the difference quotients? Okay. So make sure graded homework is sent to me today. What we'll look at right now then is we'll go ahead and go into the practice exam. Did you guys grab one? So whether you've printed one out or you prefer to look at it offline, either way it really doesn't make a difference to me, and I'll have it up here as well. So I'm just going to highlight again here the important parts through the section. We'll look at all the questions together, then we'll start attacking some of them as we go through and get as many covered as we possibly can. So let me go ahead and get rid of this now as well. So again, Chapter 2 started off with looking at the concept of limits as x approached a certain value. And then we even broke it down into the individual one-side limits as we look at as it approaches from the left-hand side and the right-hand side. Now, as we look at number 1, these are all two-sided limits. Okay, we're not looking at any positives or negatives up above those, so these are two-sided limits. Now, we always attack a limit first by using what? Direct substitution. We're going to just take that value that they've given us and plug it in for x and see what we get. Okay, but what's the clue that direct substitution isn't going to work? A 0 in the denominator. If you get a 0 in the denominator, that clues us into we've got to do probably some kind of an algebraic method. And we looked at that worksheet on the algebraic methods. The first one said just simplify things down if you can. You know, expand out squares, combine complex fractions. Okay, so do the algebra, simplify things down. Number 2, like what A here is probably looking at, is we could probably do some what? Factoring. Okay, simplify things down algebraically, factor. It doesn't look like we've got one up here, but if you see radicals, you might want to try to do what? Rationalize. Yeah, multiply by its conjugate. We'll rationalize if we can go through those. Okay, so that's what number 1's looking at, are just those basic concepts of limits. Now, here in D, we've got a limit as we go off to infinity. Okay, so that's kind of looking for a horizontal asymptote, or an end behavior model if we have one. Let's go ahead and take a look at, let's look at C. Not only do we have algebra here and C, but we've got some trig as well. Let's take a look at C together. And now on the test tomorrow, I'm going to ask you to find them algebraically, and then you can confirm them graphically or numerically. But the points are going to come from the algebraic method here. So x cosecant x plus 1 over x cosecant x. Now again here, I can look right away and say direct substitution here is not going to work. In the denominator, I've got x times something. Well, if x is 0, 0 times anything is going to be 0. So a direct substitution is not going to help me out here. We've got to see if we can possibly do something. And what I'm going to look at is just the algebra of this. How many terms do we have in the numerator? There's 2 terms. So what I'm going to do is I'm going to split this fraction into 2 fractions. I'm going to look at the limit as x approaches 0 of x cosecant x over x cosecant x plus 1 over x cosecant x. If we're going to add 2 fractions together, they have to have a what? Common denominator. So I recognize that here, and I split this denominator into both parts and have this now. Okay. Will this help me out now? Yeah. What do we have over here? 1. Okay, that's just simply 1. So we have the limit as x approaches 0 of 1 plus 1 over x cosecant x. But we've still got that issue of having the 0 in the denominator. And again, if we wanted to, we could split this into two limits. The limit as x approaches 0 of 1 plus the limit as x approaches 0 of 1 over x cosecant x. Okay, so this one's taken care of now. This one over here is fine. This limit, no matter what x is approaching, we've got a constant. This over here is always going to be equal to what? 1. Yep, that's always going to be equal to 1. But over here we still have that issue of the x in the denominator. And we've somehow got to get that factor of x to cancel out. And what am I overlooking here? We've got to get that factor of x to cancel out somehow. Cosecant x is 1 over sine x. So let's do that. Let's see if we can simplify this out here. Let's turn that x, or that cosecant x, into 1 over sine x. So in the denominator, then, what is x times 1 over sine x? X over sine x. So that whole denominator there would become x over sine x. And then how do we divide by a fraction? How are we going to divide by x over sine x? Multiply it by its reciprocal. So this here is really 1 times sine x over x. So as we keep going with this one here, it would be plus the limit as x approaches 0 of sine x over x. And that's that important one that I had you write down. As x goes to 0, sine x over x approaches what? 1. That approaches 1 as well. So our limit here as x approaches 0 would be equal to what? 2. 1 plus 1 gives me that limit of 2. Let me explain this one a little bit more, because I know I didn't the last time. The limit as x goes to 0 of sine x over x. As x goes to 0, what does sine x approach? If you were to look at that graphically, yeah, it goes to 0. If you remember, sine looks like this right here. So the limit of sine x as x goes to 0 is 0. Okay, as x approaches 0, we are getting closer and closer and closer to 0. But again, we're not concerned at 0. We're not looking at the function value. We're looking as we get closer and closer and closer to 0. Well, how about I put this graph up here as well? X is just the identity function that goes through like that. Well, what happens to x as x gets closer and closer to 0? It goes to 0 as well. Now notice, in this neighborhood right here of 0, are those two graphs pretty much exactly the same thing? Yeah, in that neighborhood right here, very close to 0, those two graphs are pretty much the same thing. Which basically means I've got a quantity that's being divided by what? Itself. The black and the blue here are basically the same quantities. And again, we're not looking at 0, we're looking as we approach 0. So as we're right here, the black and the blue function values are pretty much the same. As we look up here, the black and the blue function values are pretty much the same. Anything divided by itself is equal to 1. So that's why this limit right here is equal to 1. Again, we're not looking at 0. We're looking as we approach 0. Well, as we are very close to 0 here, these two functions are the same thing. And anything divided by itself is always going to be 1. So that is why the limit as x approaches 0 of sine x over x is equal to 1. We really can't get it algebraically, and that's why I had you write it down as an important limit. And that's why it's equal to 1, because it's basically the same thing divided by itself. Anything divided by itself will always be 1. Okay, now with y sine x over x as x approaches 0 is equal to 1. Does that make a little more sense now than just what I told you at the beginning of why it's just 1? And I kind of give you the verification of it here now. Okay, so this limit would be equal to 2. Now, if we're not sure, now I don't recommend this tomorrow for every single limit question that you have on the test, but for the ones that you're not sure of, could we go and check this graphically or numerically? Yeah, what I'm going to do is I'm going to go ahead and go to the calculator. Very important here that I'm in what mode? Radian. Yep, with trig, we've got to make sure we're in radian. So just do a quick check, and I'm not. I'm in degree. So I'm going to turn it to radian. And then I'm going to go to y equals. Now, normally, in Algebra 2 and in pre-calc, if you wanted to type in cosecant into your calculator, what did you have to do? 1 divided by sine x. Do we have to do that anymore? No. Where can we get those reciprocal trig functions now? Hit the math button twice. Yep. So I've got a fraction here, so I want my numerator in parentheses. So we're going to go parentheses x, and then I hit math. Right there's cosecant number 1. X, cosecant x. Make sure you close off the x with the cosecant. Plus 1, there's my numerator, divided by, open the denominator, x, math, option number 1, x, cosecant x. Again, I don't like to look graphically. I think it makes more sense to me personally to see the data table, the table of values. That makes more sense to me. So I'm going to go into my table set. And I want my table to start at 0. We're looking at the limit as we approach 0. So I want the table to start at 0, and I'm going to increment by 0.001. We want values of x that are very close to 0. We'll go second graph, which is my table. And again, we've got the error there. We knew that. That was fine. But as we approach 0 from the left and the right, we can clearly see here that our limits are 2. Now, are these function values exactly 2? No. What's happening over here is the calculator can't display the decimals, but if you were to go over here, is it really 2? No, 1.9999985. Getting closer and closer to 2. Okay? It's just, again, the calculator can't put in that little space that's provided here in these tables. The calculator can't even put the scientific notation, so it just rounds it off at 2 instead of saying something e to the whatever. Okay. Graphically, I would set my window up to surround 0, so probably -2 to +2. We think we had a limit of 2, so I would surround probably like 0 to 4. And as we graph that off, take a while because of the cosecant function. Now we're not going to see the gap here because we got the x-axis, or I'm sorry, the y-axis there, but there should be a gap right there. And when I hit trace, you'll see that there's a gap there, that there's not a function there. But can we clearly see that we are approaching 2 from both sides on the graph as well? Yep, absolutely we can. Now if I were to hit trace, I have the coordinate 2, 4 centered. So when I hit trace, that's where the spider should automatically go. And we see that there is no function value. But again, is that what a limit is asking you? No. It's not what the function value is. It's not what is the value at 0. It's what is it approaching? What is it around 0? Okay with C? I'd also like to recap D as well, and just recap what that quick trick is with rational functions as x goes to infinity. So when we're dealing with limits as x goes to infinity, there's a couple things we can look at, and I think the easiest trick is to divide all of our terms by what in this particular case here? Yeah, x squared. We're going to divide everything by x squared. The highest power of x from the denominator. Okay. So this is going to turn into the limit as x approaches infinity of 2 plus 3 over x squared over 5 plus 7 over x squared. Now, why did that help me? Why did I want to divide everything by the power of x? Because we know that the limit as x goes to infinity of any constant over any power of x is going off to what? They're going off to 0. You're taking a number and dividing it by an extremely large number. Well, that number is getting smaller and smaller and smaller. It's getting to 0. So these both knock out as zeros. And it gives me a limit of 2/5. There's really no direct substitution here when you're going off to infinities. You've got to think conceptually. Okay? So that's one trick. Now, the other trick in the book, now I would always do this with rationals. If it's a rational function, I would always do this. But in the notes and in the textbook, they also gave you another way to determine or look at limits as x goes to infinity. What they said is, if we're looking at the limit as x goes to infinity of some function f of x, well, ultimately it's the same as looking at the limit as x goes to 0 of our function evaluated not at x, but at its reciprocal, 1 over x. Looking at a limit as x goes to infinity of some whatever function is the same as looking at the limit as x goes to 0 of that function evaluated at 1 over x. Okay. Now, using this method here really makes these ones more difficult. But if it's not a rational function, like if it was an exponential or a logistic or something like that, that makes this one a little easier. Let me try and find an example from the text of that one. This would have been back in 2.2. I'm pretty sure there was a section that they wanted you to do that in. In this section right here, in 49 through 52 here, I'm looking at page 76. They say use the graph of y equals f of 1 over x to find the limit as x approaches infinity on these ones here. So let's go ahead and take a look at this one. Let's look at like 50 here. So here they want me to find the limit as x goes to infinity of our function f of x, which is x squared e to the negative x. Well, can we do that quick trick that we did up here? No, because there's no value of x in the denominator. Okay, so we can't use that quick trick here. So what we can do is look at this as being the limit as x approaches 0 of this, but with our x replaced with 1 over x. So it's going to be 1 over x squared times e to the negative 1 over x. And now we can go with a substitution here. Okay. So 1 over x is x goes to 0, and then we square that off. This over here, as we go to 0 as well, that's not going to help us very much, is it? We're getting the undefines on this one. Let me do this first here. What do negative exponents do? What would be a way of me writing e to the negative x without using a negative exponent? Very good. 1 over e to the x. So this is x squared over e to the x. X squared over e to the x. So let me look at it that way then. And now I replace my x with 1 over x. So this would be 1 over x squared divided by e to the 1 over x. So this would be really equal to the limit as x approaches 0. And maybe I'm looking at this one too deep. They wanted me to use the graph of this one, so maybe we can't look at this one algebraically. Maybe we do need the graph. Dividing by this is multiplying by its reciprocal. So it would be 1 over x squared e to the 1 over x, which we're getting zeros. There's no way to help it. Yep. So I'm trying to kick a dead horse here. We really can't evaluate this one algebraically. We'd have to look at this one graphically. Okay. But again, if you're graphing something, looking at the limit as x goes to infinity, that's still you got to keep scrolling way out as opposed to just looking at 0. So here we've got 1 divided by the quantity x squared e to the 1 divided by x. Make sure I've got everything closed off here. Boom, we do. I'm just going to do a zoom 6. We're looking at as approaches 0. I've got nothing showing up. Okay, so yeah, we can zoom in a little bit. It's taking forever to graph this morning. If I go to zoom, I want to zoom in. I'm going to zoom in right here at 0, 0. Okay. So over here to the left-hand side, as we approach 0 from the left-hand side, my function values are going off to what? Yeah, positive infinity. But over here, as we approach from this right-hand side, we can see that our limit is going to 0. Our limit's going to 0 over here. Okay, we've actually got a function value of 0. So the limit then as x goes to infinity, positive infinity, is looking at from the 0 side, or the right-hand side. So this limit would be equal to 0. The limit as x goes to negative infinity of that function there would be equal to the infinity. Okay. So as we go out to positive infinity, we're looking at the right side of 0. As we go off to negative infinity, we're looking at the left side of 0. Okay. So those would be our asymptotes there. Again, if we can use the quick trick up here with the rational functions, it's a lot easier. If not, we can kind of look graphically as x goes to 0 of our function evaluated at 1 over x. I want to come back up to this one again, though. So since there is a limit as x goes to infinity, then what can we say about the line y equals 2/5? What does that line y equals 2/5 represent? It's our horizontal asymptote. It's our end behavior model. So if there is a limit as x goes to infinity, then that's our horizontal asymptote. Y equals 2/5 would be our horizontal asymptote. It would also be our end behavior model. Okay, as x goes to infinity, our y's are approaching 2/5. Okay with those two limits? Number 2, we've seen this a couple times then. We've got a function over here. Can you clearly see the open versus the closed circles? Okay. So they're just asking some two-sided limits, some one-sided limits, so on and so forth. And 3 goes along with this graph as well. They're asking you about being continuous. Again, if the function's going to be continuous, then the limit and the function value have to be the same. So as we approach from the left-hand side, The limit has to exist as we approach from the right-hand side. The limit has to exist, and the function value has to exist, and they all have to be equal to each other. Okay, if they're all met, then it's continuous. If not, we've got discontinuities. Okay. Now, tell me then, please, what kind of discontinuity do we have here at B? Removable, yeah, because we could patch it and make a gap. What kind of discontinuity do we have at C? A jump discontinuity at C. Okay. Same type of question here on 4. Number 5, they're finding any vertical asymptotes. So in number 5 here, then, where will there be a vertical asymptote? X equals... Yeah, x equals -2. Why at x equals -2 will there be a vertical asymptote? Yeah, it's where it's undefined. It's where it's undefined. So part B then, describe the behavior to the left and the right. So they just want you to find the limit as x approaches -2 from the left and as it approaches from the right. And what you just need to verify is that they're going off to the infinities. So when we have a limit that's equal to infinity at x equals a, then that gives us then that vertical asymptote. 6, we've got a piecewise function. They want to find the right-hand and left-handed limits as x approaches 1. So which function will we have to use for the left-hand limit? Which part of the piecewise function will we have to use for the left-hand limit? The top one, the absolute value. For the right-hand limit, the bottom one. Which function will we have to use to find the function value at 1? The bottom one. Why the bottom one? Because that's where it's equal to 1. And then they're going to ask, is it continuous or not? So on and so forth. N behavior model and any horizontal asymptotes for this one. So again, in 7, we're really trying to find the what of f of x. If we're going to find a horizontal asymptote, what do we want to find of that function f of x? The N behavior. We want to find the limit as x goes to infinity of that function. So just like we did up in 1D, okay, we want to find the N behavior model, or the limit as x goes to infinity. We had a couple, like number 8 in a recent homework assignment. What value should we assign to k to make this continuous? So what we're worried about here is that x equals 0. We need to find the limit as x approaches 0 from the left-hand side and from the right-hand side, and see what that value of k needs to be to make it continuous. Okay. Number 9, average rate of change. How do we find the average rate of change? That's just simply computing a what? A slope. So we are going to find the coordinate at 0 and the coordinate at pi, and we're going to find the slope of those two coordinates. Okay. Average rate of change is the slope of the secant line. Okay, so we're going to find those two function values and find the slope. Versus instantaneous rate of change, which is the same as the slope of the curve and the slope of the tangent. Number 10 here, how do we find the slope of a curve? M equals limit as h approaches 0 of f at x plus h minus f of x all over h. The limit as h approaches 0 of this difference quotient, tell me the three things that it represents. Slope of the tangent line, the slope of the curve, and the instantaneous rate of change. So if they ask to find the slope of a curve, the slope of a tangent line, or the instantaneous rate of change, you're using this right here. They all represent the same thing. So part A here, they're asking you to find the slope of the curve at that point x equals 1. Then they want you to write the equation of the tangent line, the equation of the normal. How do you write the equation of the normal? We use the same coordinate, but what do we do for the slope? The negative reciprocal of the slope of the curve. We saw this, I think, in the graded homework last night. At what points, if any, are the tangents to the graph horizontal? Well, if the tangent line is horizontal, that means its slope has to be what? 0. So we take that limit, and we have to set it equal to 0 and find out, if any, what values of x will make it be 0. Okay. So on and so forth. Now, I didn't provide you with like a question that we had on the graded homework last night, the very last one. I really didn't give you an application one. But looking at number 9 then from last night for a motorcycle traveling, find the instantaneous rate of change. Folks, they don't necessarily have to say instantaneous rate of change. If they say just rate of change is instantaneous rate of change. Okay? If they want to find the average rate of change, they have to state average. If they just say rate of change, that means the instantaneous rate of change. Okay? So be prepared for one like that on the exam as well, to be able to find an instantaneous rate of change. What was the speed of the rock at time 4? What's the velocity or speed of the motorcycle at time whatever? Okay? So see those ones as well. Again, understanding that concept, that limit of the difference quotient means all 3 of those different things. Let's go through 10 together. Go through the different parts on 10 with the time we've got left. I'll have you walk me through it. Before we get out of this one here, folks, before I lose time, if at all possible, I want to encourage you to get on to the Adobe Connect tonight at 7. I'm presenting to the Board of Education tonight using the Adobe Connect. So the more traffic they see on there, the better it's going to be. So I'd encourage you, if you can get on tonight, please try. The board meeting starts at 7, and I'll probably be presenting around 7:05 to 7:10. So if you can get on, go ahead and do it. And what I want you to do is I want you to blow up the chat. I want a lot of chatter going on. I want the board members to see that you guys are using this and bang, 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 chatting back and forth, so on and so forth. I want to see that get blown up. A big reason that I want to present this to the board is because it makes the hour distance between especially Sherman and us, that gap is completely closed now. Okay, you guys have as much access to me as my students do. And the same thing for you, John and Hinsdale, as well. That gap is basically out. I might even, depending on microphone type-wise, I might even have you guys just say something as well. I wouldn't put you on the spot, though, if you wouldn't want to, so that's fine. But, I might throw a chat to you as I'm presenting and say, hey, does anybody want to say anything or anything like that? Okay? Your microphones will be disabled and your cameras will be disabled. I don't want to take the bandwidth of the meeting room and make it so it's choppy. So be on there if you can. Chat amongst each other, just so they can see a lot of activity going up on the Adobe Connect as we're there. Okay, so if you can tonight, please go ahead and get on. And then after the board meeting's done, I'll just stay right here, and if we do have math questions, we will gladly go over those, seeing that we've got the test tomorrow. Okay? So if you can tonight, please go ahead and try and get on. Okay, and to number 10 then. So let f of x, we've got this quadratic 2x squared plus 3x plus 1. We're looking at the point 1, f of 1. So let's take care of that right now. What is the function value at 1? So 1 squared is 1 times 2 is 2, plus 3 is 5, plus 1 is 6. So point P is really the coordinate 1, 6. So they want me to find the slope of the curve at point P. Well, before I find the slope of the curve at point P, I'm going to find the slope of the curve anywhere. M is equal to the limit as h approaches 0 of our function f evaluated at x plus h minus f of x over h. Now please use parentheses and brackets here to help you out. So we're looking at the limit as h approaches 0. And then I'm going to bracket off the f of x plus h. What will our function look like with the x plus h substituted in? 2 parentheses x plus h squared plus 3 parentheses x plus h plus 1 minus bracket off the f of x. 2x squared plus 3x plus 1 all over h. And now here is where the simple mistakes happen. Folks, there is a lot of room for error on here. Okay, so if you need to write it all out, write it all out. Take it step by step. Don't overlook something as simple as distributing a negative, because that'll throw the whole thing off. So again, what is x plus h squared? X squared plus 2xh plus h squared. But what will we get when we distribute the 2 to it? 2x squared plus 4xh plus 2h squared. Distribute the 3, we'd get plus 3x plus 3h plus 1. Now over here, there's nothing for us to evaluate. We just got to distribute the negative to all three of those terms. Minus 2x squared minus 3x minus 1, all still over h. And this is still the limit as h approaches 0. You've got to be very consistent with your notation here, folks. Don't get lazy on the notation and get in that habit, because when you get to the AP exam, you don't want credit taken off for bad notation. Okay. What's going to happen to all my non-h terms? 2x squared, negative 2x squared. 3x, negative 3x. Positive 1, negative 1. They all drop out. So I'm left with 3 terms up in the top, and they all contain an h. So what are we going to do with that h? We're going to factor it out. What would be left of the 4xh? 4x. What would be left of the 2h squared? 2h. And what would be left of the 3h? 3. And now what will happen to the h's? They're going to cancel out. We're really looking at the limit as h approaches 0 of 4x plus 2h plus 3. And now that h from the denominator is canceled out, we can now evaluate this limit with what? Direct substitution. What's going to happen to this 2h? It's going to be 0. So the slope anywhere on the curve will be defined by what? 4x plus 3. Now specifically, we want at x equals 1. Well, at x equals 1, y we determined was going to be 6. And our slope is going to be 4 times 1 plus 3, which is equal to 7. What's the point slope formula if we're going to write the equation of a tangent? Slope x minus x1 plus y1. So the equation of our tangent would be y equals 7 x minus 1 plus 6. Now, is it necessary to simplify that down? No. Okay. How about the equation of the normal? The normal would be y equals the x minus 1 plus 6 is still going to be the same, but what do we have to do with the slope? Negative 1/7. So on and so forth. Okay. Could I quickly and easily now find the equation of a tangent anywhere else on that line as well? Yeah, because we know the slope anywhere. Once we know the slope anywhere, it's easy to plug in any x value to find out what the slope would be at those spots. Okay with that one, folks? Good there? Okay. Now in question number 11, once we get it down to the slope, once we would get this 4x plus 3, we would set it equal to what for a horizontal tangent? 0. Yep. You'd set it equal to 0 and find that xy that we give it to us. Questions at all, folks, before we break for the day? Okay. So look through your practice tests tonight. You got the solutions there. Again, we'll have review session again tonight from 7 till whatever time. Again, just probably from 7 to 7:30 will be board meeting. But again, please go ahead and get on and chat it up. Okay? All right, folks, we will see you tomorrow morning. It's just going to be tests tomorrow. After the test, I'll ask you for an assignment anyway to start reading 3.1 and make the connection from what we had in 2.4 into the concept of the derivative in 3.1. So for Monday morning, I will expect that you have read 3.1. You'll have glanced through the notes and you'll have seen the examples that we're going to go over out of 3.1. But class-wise, test. When you're done with the test, you're done with class. Okay, folks? Have a great one, and we will see you tomorrow morning.